Hello, good afternoon. So for today, I am creating a video lecture to augment our learning with regard to the problem solving involved in filters. So I have already mentioned or I have already sent to you the audio lectures for the concepts in active filters for part 1 and part 2. So this time around, let's look into things that we need to solve or to be able to calculate when we look into filter design. So one of the most important things that we need to look into, kasi one of the defining characteristics of a filter is its cutoff frequency. The cutoff frequency dictates which sets of frequencies are allowed to go to the output and which are blocked. And that is true for all types of filters, from passive to active, from the low pass, high pass, and band stop, from Bessel, Chebyshev, and Butterworth. So, with that being said, we will be focusing our attention on the cutoff frequency, okay, which is this one. So, cutoff frequency is 1 over 2 pi RC, R being the resistance and C being the capacitance in the filter. Okay? So let's take a look into the low pass filters and see how we will be able to use this. So as mentioned, this is what the low pass filter design look like. So the output is in parallel with the capacitor and in series with the resistor. So that is reversed in a high pass filter. So I've discussed that already with the audio lectures. So depending on the value of the resistance and capacitance here, we would be able to determine the critical frequency. By the way, I just have to reiterate, the critical frequency is the frequency in which the gain of the signal would be half. Okay? So let's look at a specific example here. Okay, just a moment. So let's say we are to calculate the frequency of a low pass filter given a resistor value of 1 kilo ohm and a capacitor value of 0.22 microfarad. So as mentioned, our critical frequency is equal to 1 over 2 pi RC. So the resistance is given. The resistance was equal to 1K or 1 kilo ohms. Okay. And the capacitance is or was equal to 0.22 microfarad. Okay. So we just have to substitute both the resistance and capacitance to the formula. So that means we would have something like this. So still have the 1 here, then 2 pi, and then the 1 kilo ohm multiplied by the 0.22 microfarad. So using our calculators, so we have your 2 pi, 1 kilo ohm, and 0.22. One way of doing this is we could compute the 2 pi or everything in the denominator, then put in the reciprocal. So I'll be doing just that. So that will be 2 times shift pi multiplied by 1 exponent 3. Remember that kilo means exponent 3. Multiplied by 0.22 microfarad. Microfarad is exponent negative 3. So we'll get an answer of 11 over 25 pi. Let's get the reciprocal of that. That would be 0.723. Kaya I think I made a mistake a while ago. Let's go back to my answer. Kasi parang 3 yata yung nailagay ko, or negative 3 nalagay ko sa microfarad. Let me just repeat that. So 2 times pi times 1 exponent, oops, I forgot the parentheses, 1 exponent 3 multiplied by 0.22 exponent negative 6. Okay, so we have this, and then so that means we have the answer would be 723.43. 723.43. What would be the unit? Because this is frequency, the unit would of course be in hertz. Okay. So let's take a look at another problem. So this time around, what we have is not a worded problem, but the design of the filter itself. Now, do you still remember what type of filter this is? Okay. Anyway, 50-50 lang naman yan. It's either a high pass or a low pass. But do you still remember? Okay. So, just to remind you, let's take a look at the low pass and high pass again. So, a low pass has a capacitance in parallel with the output. If it's a resistor, then it's a high pass filter. So, going back to the problem, we will be able to see that because the resistor is the one parallel to the output, it is a high pass filter. Okay? So we are to calculate its cutoff frequency. So same formula. So 1 over 2 pi RC. But this time around, our resistor is 1.5K. And our capacitance is 0.1 microfarad. Okay. So let's just delete this to avoid confusion. Okay. And my favorite keyboard shortcut, Control C, Control V. Best of all time. Okay. So let's try computing it again. So again, I'll be computing the denominator first, then get the reciprocal. So 2 times pi times quantity 1.5, because this is again kilo, exponent 3, multiplied by 0.1 exponent negative 6. That would give me an answer as shown on the screen. Then I'll just get the reciprocal. And the answer is 1061.032. Again, because there are 4 whole numbers here, we click ENG. So we get 1.06 times 10 to the 3. So that would be 1.06 times 10 to the 3 is of course kilo, then hertz. Okay, so the answer would be 1.06 kilohertz. Okay. So this time around, after getting the cutoff frequency, we can actually compute or calculate the effect of the frequency on the output power, voltage, or current. So that is what we're going to use in order to answer this question. A circuit consisting of a resistor of 4.7 kilo ohms is in series with a capacitor of 47 nanofarad. Okay? And it is connected across a 10 volt sinusoidal supply. Calculate the output voltage at a frequency of 100 Hz and again at a frequency of 10 kilohertz. So in order to be able to answer this, we would now be needing the other formulas aside from this one. So we're being asked to get the voltage output. Okay? In order to get the voltage output, it is actually a factor of X sub C over Z multiplied by the input voltage. In this case, that would be 10 volts. So we need to be able to determine X sub C. X sub C is 1 over 2 pi FC, almost similar to this one, but R and FC were interchanged. Okay? So what we're looking is the capacitive reactance. Okay? Then once we get this, we need to determine the impedance. Impedance is the opposition to alternating current. So as you can see here, it looks like the Pythagorean theorem. Okay. Now if you're going to study circuits too, you'll learn why it looks like the Pythagorean theorem. But in our case, this is enough. Okay. So we need to get X sub C, then get Z, then we'll be able to use or get the output voltage. Okay. So let's go to our board. Let's erase everything here. So it's mentioned that X sub C let's technical problems. Okay, so again X sub C is equal, that's a problem with new software. I don't get to seem to, yeah, there we go. Is equal to 1 over 2 pi FC. Okay. So let's determine X sub C first. So in this case, from the problem, we were given two frequencies. Okay. Let's determine the first one. So our capacitance is 47 nanofarad and the first frequency is 100 Hz. Let's take a look at that. So capacitance is, God, I forgot. There we go, 47 nanofarad. Sorry about that. And then we have the frequency, which is 100 Hz. And we are to determine X sub C. By the way, X sub C is in ohms. Okay? So let's take a look. It's equal to 1. Oops. Let's just delete F and C. So 100 Hz again, multiplied by the 47 nanofarad. No, not there. Here. Nice. And let's take a look. And let's compute again. 2 multiplied by pi multiplied by 100 hertz multiplied by 47 nanofarad. Nano is -9. Uh, Wait, that's not clickable. Let's not forget our parentheses. It's not clickable. That's the one. Then we get the reciprocal, so we get this. Okay. Again, let's not forget to press ENG for engineering notation. So that will be 33.86 times 10 to the 3 is kilo, so kilo ohms. 33.86 kilo ohms. Okay. Now we need to get Z, or impedance. Okay. Impedance would be the square root of R squared plus X sub C. Wait, you need to be inside. Yeah. Easy. Squared. Okay. So we already got X sub C squared. So it's just a matter of substituting the given. By the way, our R, I forgot. Let me just get our R is 4.7 kilo ohms as stated here. So let's put that. 4.7 kilo ohms plus the answer that we got here a while ago. Again, I forgot to include it under the radical, or the square root sign rather, not the radical. So let's try computing that one. Oops, I forgot the squared. This should be squared. And you should be squared as well. Where are you? There you go. So 4.7 x squared plus 33.86. Wait, I forgot to put in the kilo ohms, or the K. 4.7 exponent 3 x squared. Just to be safe, let's put a open and close parentheses just to make sure that it is correct. Then 33.86 again kilo, and then x squared. So we get an answer from that. But again, I haven't included the square root yet. We can put the square root afterwards. Square root answer. So that would be 34184.64. So let's just put it here. Again, this is also in ohms. So that will be 34.18 kilo ohms. 34.18 kilo ohms. Nice. Now, once we are able to get Z, okay, we will now be able to actually determine the voltage output. So the voltage output for 100 hertz, so the voltage output would be equal to the voltage input multiplied by this guy right here and this one. Okay, so in this case we already have the values for every variable here. Voltage input was given as 10 volts. Then we're just going to substitute what we were able to get a while ago. Okay. So if I'm going to answer this using a calculator, I'm going to use this 2 first, or compute this 2 first before I multiply it by 10. Well, I have this one, but anyway, error 3.86. Okay, because they're both kilo ohms, we can actually not put in the times 10 to the 3. Okay. Again, we can only do that if they have the same prefix. In this case, they are both kilo. So that is permissible. So 33.86 divided by 34.18. So we get this. Okay. Then multiply it by 10. We get 9.91 volts. Okay. Now, we will now compute this because as mentioned from the problem, we need to compute or calculate the output voltage if the frequency was or is 10 kilohertz. So let's look at the effect of increasing the input frequency or the frequency of the signal with the output voltage. Okay, so just a moment. Let's go back. So in this case, we're just going to change this into, this would now be 10 kilohertz. Nope, that's not K, that's K. So 10 kilohertz. Let's recompute everything. So this would now be 2 multiplied by pi multiplied by 10 exponent 3. And I forgot to put in the opening and closing parentheses again. And then multiply it with 47 nanofarad. 6. Okay. So I get this. Okay. Did I put everything? 10 to the 3, 47. Nano is negative 9. So let's be very careful when... Jeez. Again, negative 9 because it's nano. Okay. So we get this. And then, because that's just a denominator, let's compute the voltage, the capacitance, the active capacitance, by doing the reciprocal. So that would be 338.63. So 338.63 ohms. Nice. Then we can recompute the R squared with the X sub C squared. Okay. R squared is still the same. I just have to change the other one. It's now 338.63. Okay. Then I'll be recomputing this. So 4.7 exponent 3 x squared plus 338.63 x squared. Then let's get the square root of the answer. So it would be 471. Let's double check what I was doing a while ago. 4.7 plus 338.63. So yeah, this would be correct. Then where's the square root of the answer? So 4.71 kilo ohms. Okay. Then we're going to use this as for getting the voltage output. There we go. So we have 338.63 divided by 4.71 exponent 3. Okay. So we have 0.72 multiplied by 10. So 0.72 or 71 or 718.96 microvolt. So microvolt. Oops, this should be, yeah, there we go. Okay. So 718.96 microvolts. So it's quite small. Actually, it's very small because most probably the frequency is already above the critical frequency. That means it has been blocked or attenuated. Okay. Anyway, I'll be looking into the second part of this video lecture for the discussion of the other problem solving requirements for this course. Thank you very much and take care.